Hello, I'm Steve Murawski from the University of South Florida and the Sea Image Consortium of the Gulf of Mexico Research Initiative. Today, I'd like to talk about resilience and vulnerability in fish and fishery systems in the concept of coupled human and natural systems. Generally, when we talk about oil spill effects, we are very reductionist in terms of defining a certain concentration of a certain pollutant to a individual species and a life stage of that species over a fixed duration of time. I'd like to take a more holistic view and talk about these systems as they have evolved. So in terms of an outline of my talk today, what I'd like to do is define what a CHAN is. Secondly, talk about feedback loops between human and fishery systems, particularly as occurred during the Deepwater Horizon oil spill. Third, talk about how resilient the elements of a CHAN are with respect to oil spills, and particularly focus on fishery and fishery systems. And last, what lessons can we incorporate for future oil spills? So what are CHANs? A coupled human and natural system, or CHAN, characterizes the dynamic two-way interactions between human systems, that is, economics and social systems, and the natural world. This coupling expresses the idea that humans and the environmental systems are co-evolved, and they shouldn't be treated as sort of isolated actors in these larger systems. This is very different than the traditional way that biological systems are evaluated in terms of oil spill impacts. So one of the things that we can use to define the concept of chance better are a number of attributes that have been developed in the academic literature that defines them. And this paper listed at the bottom is one of the major papers that have outlined the chance concept. First of all, that effects are reciprocal and that there are feedback loops. Reciprocal in the sense that fish affect fisheries, that is their abundance, and fisheries affect fish, that is overfishing and other direct impacts. And that these feedback loops, that is, between the fishery system, human system, and between the natural system, exist, and the strength of those feedback loops is important. Secondly, that nonlinearity and thresholds exist in these systems. Oftentimes, these are termed things like tipping points. The notion of nonlinearity is that a little bit more of a certain control variable doesn't necessarily elicit a linear response. Third, that there are surprises in these systems. Sometimes these are called black swans, and that is there are linkages that we did not anticipate, particularly in relatively simple, straightforward defined systems. Fourth, that there are legacy effects and time lags. All of the things that were happening in fisheries didn't start on the day Deepwater Horizon occurred. There was long-term overfishing and habitat loss and climate change and other things. The time lags generally refer to the impacts of something like an oil spill and why it takes so long to express all of the impacts in populations, and it relates to the life histories of animals and other things. The notion of heterogeneity, and that is, we know that oil spills are not uniform over the area that they occupy, that they represent a mosaic of concentrations from zero to very high. And likewise, biological systems exist in that mosaic as well. And last, the concept of resilience, and that is what makes a species and a fishery more or less resilient to a perturbation like an oil spill, and how can human systems affect the resilience of the fish systems, and how they can affect the resilience of fisheries as well. So testing the veracity of the chance concept, there are two terms that people use to try to identify the causal interferences that occur, the causal links between things like an oil spill and the biological outcomes. And two important terms are used in these definitions. One is the term excludability, and that is if there are multiple drivers of the outcome we're trying to understand, then we don't have this excludability that you can exclude other things. Generally, it's a matter of degree. And then secondly, the term of no interference. And no interference describes the assumption that things that occur outside the spatial domain of the oil spill don't affect the things that are inside that area of interest. We know things like climate change certainly do. They occur within and outside the domains of things like an oil spill. And so one of the concepts here is that the violations of these assumptions of excludability and no interference, they complicate our ability to actually understand cause and effect, which is important. So in terms of a conceptual diagram of the causal loops between biological systems and human systems, this is a concept diagram that's being published right now by Helena Solo-Gabriel and 41 of her co-authors in Journal of Marine Policy. And it lays out a system for Deepwater Horizon, as well as some of the social outcomes are interrelated. And many of the examples that I talked about in terms of the attributes of a chance system are embedded in this diagram. It would be great if we had a quantitative model that actually, could look at the strength of the interactions between all of these things. In actuality, we know some of these causal links pretty well. There are other ones we only have a notion about the directionality and strength of them. So for example, if you look at this diagram, we know that the physical and biogeochemical aspects of the system are pretty well known and modeled. Biological systems to a lesser degree, but still pretty well known. When we get to things like the regional economy and physical outcomes and mental health outcomes, we know very little quantitatively about these, primarily because of lack of baseline information. So we have a large-scale notion of a conceptual diagram, but existing quantitative models are somewhat scarce. So I want to talk a little bit about the resilience of Gulf fisheries because it illustrates a number of examples of some of the attributes I just talked about. And so this is a 70-year history of the landings of fishes in the USA portion of the Gulf of Mexico in terms of the quantity of fishery landings in thousands of metric tons and the value of those fisheries in dollars. And so you can see, for example, there was a spike down in 2010 in the quantity of landings. And a very slight decline in the value of those fisheries in 2010, but followed by a very rapid increase in the value and quantity of landings in 2011 as fisheries were again allowed, and then the value of the fisheries spiked in 2013 and has hovered between $800 and $900 million per year. So you would call this system pretty resilient to the shocks of Deepwater Horizon and the fishery closures. So what are some of the things that happened in the human system that helped to compensate for the loss of opportunity when about a third of that area was closed? The total ex-vessel value, as I talked about before, only declined about 2% between 2009 and 2010, but then increased 30% the following year. Part of this was related to the spatial changes in the catches, where much of the catch of high-value things like white and brown shrimp were taken off Texas during that year, and so there was a bit of effort transference outside the spatial domain of the fishery. We also had compensation programs that helped to increase the resilience of the fishery system. The VU program actually paid out nearly the entire ex-vessel value in the United States part of the Gulf of Mexico for the year 2010. It was an enormous amount of money that went mostly to commercial fisheries. And then we also saw compensation for business losses of about $10.5 billion. Of course, not all of that was related to fishing, but big compensation for fishing-related businesses that were in various communities. All of this resulted in an annual business turnover rate or business failure rate for some of these fisheries significantly below historic levels. And so we can see now that some of the things that were done during the system actually improved the resilience of the fishery, at least in the short term. So one of the effects I want to talk about in a little bit more detail is the so-called legacy effect. And so on the right-hand side of the diagram, you see the relative abundance of eastern oyster as sampled in 3 of the major basin systems in southeast Louisiana and Alabama as well. And you can see that the Deepwater event is embedded in a long-term decline in oyster abundance that was exacerbated in some locations like Barataria during Deepwater Horizon. But then, because of the reduction in effort, we saw abundance increase in some areas, at least in the short term. But then, we've seen this longer-term change in the decline in abundance that does not seem to be abated. So clearly, legacy effects are important when we look at things like eastern oyster. The other effect I wanted to talk about was the impacts of some of the oil spill countermeasures, in particular the water diversions, in terms of the long-term trajectories of important fishery-related species. So on the right-hand side, you see the average environmental conditions during the trawl surveys that Louisiana Department of Wildlife and Fisheries conducts in Barataria Bay. So you can see that in the earlier part of the time series, the salinity was high, and in the later part, it was relatively low. And conversely, the water clarity has improved. On the right-hand side, what you see is that as the salinity has decreased, the incidence of freshwater species has gone up, whereas some of the more saline-dependent fishes and invertebrates have gone down, and particularly the invertebrates. And so there has been a significant freshening of Barataria Bay. And if you look at it in terms of of non-linear change in threshold exceedance, there's been a compositional change in the species composition of trawl caught species that's very significant. So between 1994 and 2009, you see sort of one stanza of species dominance. Then you see sort of a 3 years of intermediate change. And then in the more recent years, you see a much different species composition. And so this looks to be something like a threshold exceedance, and it's probably related to the freshening of the water in Barataria Bay. Now, of course, there will be other diversions much greater than the Deepwater Horizon experience in the future as part of the whole effort to rebuild the marshes in Barataria Bay. So that does not portend for reversal of this particular trend. So one of the last concepts I want to talk about was the concept of resiliency and whether or not some of the sub-ecosystems that were affected by Deepwater Horizon were more or less resilient to the spill. And so my colleagues and I, who have been working on this for the last couple of years, have parsed the system into 4 sub-ecosystems: coastal inshore, continental shelf, the open ocean, ocean water column, and then the deep benthic. And so our question is, are some of these ecosystems more or less resilient to the effects of deep water than others? And so what we did was we developed a series of criteria which get to the issue of the vulnerability of individual species to the consequence and the happenstance of Deepwater Horizon versus the resilience potential of those species. And so when we look at the vulnerability to Deepwater Horizon, it has to do with the overlap in spatial exposure, the particular sensitivity of life history stages, whether or not there's habitat shifting or these animals have a certain degree of site fidelity, which was differentially impacted, et cetera. The resilience potential are things like their lifespan relative to carrying capacity, their age at first reproduction, their fecundity, and whether or not covariant stressors are important. So for each species that we considered in those 4 different ecosystems, and we considered a number of what we would call key species, we rank them on all of these attributes within the notion of vulnerability versus resilience. And so these 4 plots outline for each of the sub-ecosystems, coastal inshore, continental shelf, open ocean, and deep benthic, a series of what we call key species, whether or not they were highly vulnerable, sort of medium vulnerability or low vulnerability to the circumstance of the spill, and whether or not they're highly resilient, medium resilient, or not very resilient. And so you can see that, for example, in the coastal nearshore, you contrast Barataria Bay dolphins, which are highly vulnerable and have low resilience, to Gulf menhaden. One of the things that you see in this diagram is that for all of the different sub-ecosystems, there are an array of species, some of which are not particularly resilient and highly vulnerable, and some which are not particularly vulnerable and highly resilient. And so there are really, it doesn't seem to be anything per se about these ecosystems that make them more or less resilient. This could be an effect of actually picking these species, but nevertheless, there's not a lot of contrast in these. So to summarize briefly, the science of oil spills tends to be disciplinary and reductionist. Multiple simultaneous drivers can act synergistically or in opposition, resulting in these nonlinear trends, and that makes attribution difficult. Large-scale spills like Deepwater require system-level approaches to really understand the interaction between ecological and human systems. The Chan's format seems to be a good candidate for these. And if we want to move from conceptual to quantitative format, it will require moving to more integrated, multidisciplinary science. With that, I'd like to acknowledge Gulf of Mexico Research Initiative, National Academies, and then the National Science Foundation Coastal Seas Program. Thank you very much.